For quite a while, people have envisioned what life might be like in other universes. Thanks to the James Webb Space Telescope, the most shocking telescope in existence, that question can at last be investigated. While observing the nearest star system to us, Proxima Centauri, which is just 4.2 light-years away, researchers have noticed a few extraordinary eccentricities from one of the planets in the system, Proxima B. These eccentricities, called artificial lights, have perplexed the best minds in the field of science. At any rate, what are they? Do these lights suggest the presence of intelligent life? Join us as we take a look at the James Webb Space Telescope's unsettling city lights discovery that could change everything. The only life that we are currently aware of is on Earth. Since the beginning of human civilization, people have wondered whether there is life elsewhere in the universe. To answer such an interstellar question, American cosmologists Jill Tartar and Thomas Pearson launched the search for extraterrestrial intelligence SETI project in 1984. The primary goal was to gather spaceborne radio transmissions. Radio waves can travel farther and are therefore more likely to be detected by the 42 radio telescopes that make up Allen's extraordinary array of telescopes in the Lower California region mountains. But for more than 30 years, no notable extraterrestrial signals had been found. Following that, the James Webb Space Telescope's successful launch assisted the effort to examine a range of invisible planets orbiting distant stars. As the largest telescope on the planet, approximately 1 million miles from Earth and equipped with highly sensitive detectors, it has the potential to uncover massive revelations. A few decades ago, there were no known planets outside our solar system. However, since then, more than 4,000 exoplanets have been discovered orbiting different stars. As outlined by NASA, the universe could contain trillions of exoplanets, the earliest indications of something happening far beyond our solar system might be seen in extraterrestrial vegetation. The Galileo spacecraft, on its way to Jupiter, turned its instruments back toward Earth and saw a clear sign of the presence of plants. Recognizing the vegetation red edge, a biosignature, a blend of red and infrared light reflected by plants. For a planet like Earth that is covered in wild vegetation, it should have a marked area of strong signals easily recognizable. The JWST will measure the VRE vegetation red edge of faraway Earth-like planets in the habitable zone around stars, which could provide critical indications of something occurring in the exoplanet's atmosphere. When light crosses a planet's star boundary, the JWST may be able to detect it as it enters the planet's atmosphere. The missing frequencies would then be visible through spectroscopy, as particles and molecules in the air absorb specific frequencies, creating a characteristic fingerprint that the JWST can recognize. This method could be used to determine the composition of the atmosphere and whether or not life can be sustained. Planets the size of Earth could support life with atmospheres like our own, characterized by a mix of oxygen, nitrogen, and carbon dioxide. By searching for things that aren't usually present, even intelligent life can be detected. For instance, chlorofluorocarbons CFCs, made for use in refrigeration and products for cleaning, would almost certainly be detectable by extraterrestrials studying Earth's atmosphere from a distant location. If CFCs are discovered by the JWST in planetary atmospheres, it could indicate the presence of life. However, life on exoplanets likely won't resemble life on Earth in any capacity. In some cases, even typical living organisms like extremophile species that can survive in conditions where other organisms would perish may appear alien. This group of life forms, mostly microorganisms, can survive extreme conditions, such as temperatures up to 250 degrees Fahrenheit, or strong acid with pH levels below 3. Since planets are more likely to support life, they don't experience high temperatures or acidic environments. It may be prudent to start with those first. Prime candidates could have temperatures that allow liquid water to exist on their surfaces and orbit a stable star. Our Sun is a yellow G-type star. These stars are rarer and usually have shorter lifespans. Nevertheless, in our galaxy, the odds of finding planets orbiting red dwarf stars, which are more common, cooler, and dimmer than our Sun, are higher. This long longevity allows for the growth of life and evolution to produce complex organisms, about 40 light-years from Earth. The TRAPPIST-1 planetary system will be the subject of the JWST's first mission. It orbits a quiet red dwarf star with 7 Earth-sized rocky planets. 3 of these rocky planets in the so-called habitable zone could have liquid water on their surfaces. Despite its lighter, colder mass in comparison to our Sun, a single TRAPPIST star produces light like that of Earth, which is enough for the close orbit of its planets, the most likely opportunity to observe city lights. Outside our nearby planetary system is Proxima Centauri, a red dwarf star that is 4.25 light-years from the Sun. Proxima is generally fainter than the Sun, so a planet would need to be much closer to it than Earth is to the Sun to support life based on liquid water. Astronomers discovered in August 2016 a planet with 1.3 Earth's masses in this habitable zone, a Goldilocks-like zone where the light intensity is ideal for liquid water. Proxima B orbits Proxima Centauri. But the fact that Proxima B is tidally locked makes it a potentially airless, dead planet because it revolves around its red dwarf star just 4.6 million miles away. This close orbit exposes it to strong solar winds that can strip away its atmosphere. However, Proxima B receives enough light for temperatures and liquid water like those on Earth due to its proximity to the star. Proxima B is believed to be tidally locked, meaning it always shows the same side to the star. Much like the Moon does in relation to Earth, Proxima has about 18% of the total mass of the Sun and produces considerably less light than one might expect for a planet so close to the star, about 5% of the Sun's power. This would seem like a desolate wasteland, but liquid water could exist on Proxima B if the planet has an atmosphere to retain heat. Since the sum of all the energy coming from the star is only 65% of what Earth receives, the planet is not particularly favorable for life. It is likely tidally locked, meaning it always faces the same side toward the star, creating a permanently hot side and a cold, dark side with extreme temperature variations. The planet also receives about 5 times the high-energy radiation that Earth does, including X-rays and ultraviolet light, due to its proximity to Proxima Centauri. Proxima B is also bombarded with high-energy particles during stellar flares. Unless it has a magnetic shield field like Earth's, conditions may not be suitable for life despite these harsh conditions. Conditions on Proxima B may still make it a more habitable world. Unfortunately, models suggest that orderly environments on tidally locked planets may be prone to rapid erosion due to the freezing out of volatile gases on the night side. Earth's atmosphere can be brought back to life by volcanic activity, and for planets with strong magnetic fields, their atmospheres are less likely to escape. Given that we know nothing about Proxima B's volcanic activity, magnetic field strength, or activity, we cannot even speculate whether the planet has an atmosphere. However, since an atmosphere suggests the possibility of life, we are eager to learn if Proxima B has one. It could have solar panels on the day side to produce light-generating power and heat the night side, which would otherwise be too cold and dark for habitation. The discovery of Proxima B has sparked a race to determine if it crosses its star's face as seen from Earth. These transits would allow researchers to determine the planet's size and mass, which would help them assess its density and confirm its rocky composition. It's providing information on the materials used to form those rocks. During a transit, starlight could reveal the planet's nature by passing through its atmosphere. However, the chance that the orbit will be perfectly aligned, allowing researchers to observe a transit, is only 1.5%. The star's tendency to erupt further complicates matters. Astronomer David Kipping of Columbia University says the star is unstable as stellar heat causes a rocky planet to absorb sunlight and emit it as infrared light. However, rocky planets produce a specific type of infrared radiation from stars like Proxima Centauri. Moreover, the James Webb Space Telescope JWST was specifically designed to detect infrared light. The infrared signature of Proxima B is crucial for detecting the planet's atmosphere. Additionally, the JWST's infrared capabilities, which surpass those of the Hubble Space Telescope, could allow it to detect city lights on the night side of the planet. Even if they are as faint as those currently used on Earth, the JWST could detect artificial lighting as long as it is confined to a frequency band much smaller than the star's light. Proxima B's day side might be heavily covered with solar panels reflecting starlight, as Proxima B orbits its star continuously. The constantly shifting perspectives create extreme temperature differences between the day and night sides. The temperature contrast depends on whether the planet is made entirely of bare rock or if air and water circulate heat. If there is no atmosphere, Proxima B's dayside and nightside temperatures will vary more, as the dayside will release all the propulsion it receives from Proxima Centauri as infrared light. The nightside would resemble a frozen wasteland. If the difference in temperature between the day and night sides is less pronounced, we can estimate that space exploration in the future and the search for life beyond Earth hold enormous potential. The James Webb Space Telescope, JWST, may be the key to finding extraterrestrial life in the universe. As the JWST searches for exoplanets, it will ultimately shed light on the possibility of city lights far beyond the stars. As we continue to explore the cosmos, it's crucial to consider the limitations of our current technology. While the JWST is an incredible advancement, it is still only the beginning of our journey into deep space exploration. There are many challenges ahead in the search for extraterrestrial life. Atmospheric conditions, stellar activity, and the vast distances involved mean that we may not always get clear or definitive signals from distant planets. However, the potential for discovery remains vast, particularly as we create new technologies and refine our methods for exploring distant worlds. The exploration of Proxima B and other exoplanets continues to challenge our boundaries of understanding. Each new discovery, whether a planet with water-like features, a potentially habitable atmosphere, or even hints of artificial light, brings us one step closer to answering the profound question of whether life exists beyond Earth. With the capabilities of the James Webb Space Telescope, we may soon be able to see far beyond the confines of our solar system, looking for signs of life and perhaps even civilization in the distant stars. In the coming years, as the JWST continues its mission, we will gain more insight into the atmosphere and composition of planets like Proxima B, the telescope's capacity for locating infrared signatures, and its unprecedented sensitivity to faint signals could help us uncover not just the presence of water or an atmosphere, but signs of life, whether microbial or intelligent. It's a thrilling time for space exploration, and the potential for new discoveries is almost limitless.